Welcome to ECE 1786 lecture number 7. This is the day after I gave lecture number 6, and I've been revising lecture number 7, and gosh, it has become very large. However, this is a different way of transmitting it to you, and the way I'm going to go at this is not have an analog to having a chalkboard, which I had thought. I thought I'd write on an iPad. I'm just going to talk through the notes as I have them and point at them and circle them, because there's a lot to get through. So maybe you'll be able to pause the video if it goes a little too fast. So the work you have in flight is to figure out what your project is actually about, the topic, and to describe it well enough so that you can fill out this form that I've told you about, which is due on October 24th. The proposal document and slides subsequent to that will be due at November 4th at 9 p.m., which is the night before you're going to present those slides. I've now posted on Quirkus 2 assignments that are places where you will be able to submit those slides. You shouldn't do it yet because I need to get your group names, and I'm going to coalesce all 4 of you into your group name, and then Quirkus will know your group name. So that has to happen first. Once all that happens, I'll be announcing the scheduling of which day you're presenting on, which are the 3 possible days, and your peer review assignments. That'll all take place after the approval in principle. That's what AIP is there. Now, I also want to note that next Tuesday, although I'm not going to be there personally, this lecture is replacing that, all 5 TAs in the course will be there in that lecture room at the 9 to 11 time to help you with project ideation if you need some help cooking up an idea, given what I've said in the lecture 6. And if you've already got an idea, then it's really important to discuss the scope. Scope means the amount of things you're going to attempt to do. And the TAs will have some experience to help you get along with that. Of course, you can also reach out to your TAs because they've reached out to you by email and say which one is to tell you who they are. So that's a lot of great stuff that's good for the project. I am working on a new version of Assignment 4, which covers the decoding that I talked about in Lecture 6, and then the prompt engineering that I'm going to talk about in today's lecture, and then ultimately something that gives you some feeling for what I'm calling this year the agentic approach, which is what the Class 2 project is. I'm going to get you to do something like that. I haven't figured out yet in Assignment 4 where you're going to have 2 language models talking to each other, doing something useful. So you get that. You start to think about that. So last day, I covered language generation, which I think had that whole decoding thing, which I think is very interesting. It gives you the kind of a key element of what goes on inside the transformer architecture. And then spent a bunch of time on project ideation and described the proposal process in more detail. Today I have a lot to talk about, and it grew when I was rewriting this lecture. We're going to talk about why it's important that large language models got big, why do they get ever larger, and why they're so smart. And then we're going to talk about prompt engineering. That's what these 3 topics are about. And then we're going to talk a little bit about the use of the API from OpenAI in the projects, and something that's quite important called retrieval augmented generation. That needs a bunch of discussion. And I'm going to cover briefly tokenization and point you at the key place to look about tokenization in Jurafsky. So let's get on to it. LLM scaling. The reason we're here is that ChatGPT was amazing. That's why you're interested in it. That's why, as I said, I saw it happening before ChatGPT came out because we had access to GPT-3 and 3.5. And later, all the cousins of these of the OpenAI models from Google, Anthropic, Meta, Cohere's a local company, Pi, and Mistral. There's many of them. They came about because we made them big. That is, a lot of parameters, and the amount of data they were trained on, and therefore the amount of training that went on. And here's a table that gives you some sense of the scaling. The model that you're working on in assignment 3 uses an embedding size, the size of the input embeddings, of 48. And it only uses 3 transformer blocks with 3 attention heads on them each. And 2 lectures ago, I defined these terms, what K and H were. And this is a really small thing. And you can figure out how many parameters it is. It's in the tens of thousands, I think. That's the transformer that you're using in assignment 3. GPT-1, which isn't talked about a lot, but it came out of OpenAI, used an embedding size of 768, and the number of input tokens, maximum you could send in, were 512. It had 12 transformer blocks with 12 attention heads in each of those, and the total number of parameters was a paltry 117 million. The one that started giving everybody, making everyone pay attention was GPT-2. That's the one I mentioned. There was articles written about. It's up at 1.5 billion, 48 blocks, 1,600 wide embedding size. GPT-3 was a massive leap on that, where the embedding size is over 12,000. Remember this thing I was talking about in lecture 1? We thought maybe 50 was enough or 300 was enough. Well, these folks think it has to be 12,000 wide, which is pretty big. Context size got bigger, 2,048 tokens, 96 blocks and 96 attention heads, 175 billion parameters. And so that's a lot of gigabytes. And that's it was after that OpenAI started making things more secret. So they don't tell us this. Actually, this number has been varying a lot, from 8,000 tokens to 32,000 to 128,000, and there's lots of progress on actually the context size, which is quite important, as we'll talk about. And we don't actually know the rest of these numbers; they keep it secret, but it obviously grew. And so that's the data on the size. The anecdotal evidence, as I said the other day, is GPT-2 was the first model that spoke coherently, that it strung the sentences together just because it got bigger. But then GPT-3 began to do what it was asked to do, which is strange. Why would a computer do what it's asked to do? That's how I feel. You are used to having it happen. And then GPT 3.5, which is the basis of ChatGPT, really did what we asked. And there's a lecture I'm going to give you that explains one more thing, lecture 9, about why it does more of what we asked. It's quite interesting. And GPT-4 just got better. It got bigger, it got better, and then GPT-4o, which is available now, is, we haven't talked about it much, it's multimodal. What does that mean? It doesn't just take text in, it takes pictures in, videos in, if they're small enough, and sound in. And those are modes, right? So not just text, audio and pictures and videos. So that's, we haven't really had much time to talk about that. And maybe I should. And it also produces, as the GPT-4 produces pictures out, it can produce sound out. You can talk to the darn thing on your phone. It's amazing. That's the progress that's happened with scaling. So this is all a point to say they made a bet that scaling would make things bigger, and they won the bet. And when the GPT-4 paper came out, they put out this amazing little diagram comparing the scores of GPT 3.5 to GPT-4. So the blue lines here are the scores in a whole pile of different exams of GPT 3.5, and then the green is how much better GPT-4 was than that. And so what is this talking about here? This says this is AP calculus, high school level advanced placement calculus. The GPT-4 got a 40% on the exam. GPT 3.5 got nowheresville. Here's GPT-4 crushing the LSAT, which is the test you take in order to get into law school in North America. And so this is a passing grade, I assume, and it can do chemistry. It can do chemistry really well. It can. This is the bar exam, also a legal thing. What else we got here? AP biology, math, and so forth. What is ironic is there's something going on here. This is the AP English, which it does terribly at, which is kind of very surprising, actually. And you could ask whether there's something broken about AP English tests, or there's just something, there's a lot farther to go. Very interesting. But this is quite a stunning thing, that this single model knows how to answer tests across all this world. This thing knows more than any single human, because this isn't the only thing it can do. And I want to take this to you by asking two questions. One question is, why is it so smart? How does it know so much? And on the one hand, you might say, predicting the next word, given just a few words, well, that's pretty easy. If the sentence that we were going to train one of these models on was, the door was, and we asked ourselves, what's the next word? Well, we can easily guess that one. The door was open, the door was closed, it was shut, it was ajar. It's really straightforward. Almost anyone in this language could pick a good answer there. On the other hand, imagine you're reading a document that is talking about a complex surgery performed by a dental surgeon. Here's an example of text. Once the metal implant post is placed in your jawbone, osseointegration, a word you've never heard of, osseointegration begins. During this process, the jawbone grows into, and do you have any clue what the next word is? No, you're not a dental surgeon. These models have gotten good at predicting this next word, and the next word actually is unites. And the next part of the sentence is unites with the surface of the dental implant. And here's where you have to take in everything you know about machine learning and what you've been seeing in this course with the different models predicting the next word, which is what A3 is about, and realize if the model got good at predicting not just simple things like this, but complex things like that, then it has to know a lot. You can't just kind of guess what the next word is about unites with the surface of the dental implant. You have to know something. You have to really, truly know something. And so that, I think, is an explanation about why is the model so smart. Because we hammered on it with a method of training that worked and succeeded in predicting the next word. But to do that next word, given all these, arcane words across many disciplines, gosh, it had to know a lot. And so that's what this says. Now, I want to show you a clip from this YouTube video, which is Ilya Sutskever, very famous in our machine learning world. He did some of his training here at the University of Toronto. Here he is talking to Jensen Huang, who is the CEO of NVIDIA, a famous company for making GPUs that are underlying all kinds of these things. And at this moment in time, Jensen has just asked Sutskever, what's really going on here? And I like the way he says this, so I'm going to play it for you. I'm going to try to not make the... let's play it for you.
Knowledge and, so on and so forth.
Yeah, I can. So the way to think about it is that when we train a large neural network to accurately predict the next word in lots of different texts from the internet, what we are doing is that we are learning a world model. It looks like we are learning this. It may look on the surface that we are just learning statistical correlations in text. But it turns out that to just learn the statistical correlations in text, to compress them really well, what the neural network learns is some representation of the process that produced the text. This text is actually a projection of the world. There is a world out there, and it has a projection on this text. And so what the neural network is learning is more and more aspects of the world, of people, of the human conditions, their hopes, dreams, and motivations, their interactions and the situations that we are in. And the neural network learns a compressed, abstract, usable representation of that. Mm-hmm. This is what's being learned from accurately predicting the next word. And furthermore, the more accurate you are at predicting the next word, the higher the fidelity, the more resolution you get in this process. So that's what the pre-training stage does. But what
So I find that super interesting, and I strongly recommend you watch that whole video. You're seeing a luminary who really has thought about this for a long time and really drove the creation of GPT 2, 3, and 4. Talking about his view, it's a hypothesis of what's going on, but he's also talking about predicting the next word really well. The thing he's about to say is the subject, the thing that beyond predicting the next word, there's something that makes these things better at answering our questions. That is the subject of what I'm going to talk about in Lecture 9, actually. So, this is that's worth looking at, and that's him talking about a related view of what I was trying to say a moment ago about why predicting the next word well gets you so much more than you might have thought. Okay. A question I was kind of struggling with when I first began to teach this course, and when this capability came about, was why does a model, when you type things at it, do what you ask it to do? I mean, why? What's the command? What's the implicit thing that's going on that is why they do what you ask them to do? And again, Lecture 9 will be about how they make it better at that, but the basic model with what's called the pre-training, without the extra stuff, it will try to do what you ask. And the question is why? And my answer to that is, if you're very good at predicting the next word, and the words that come before are a question, then the next words should be the answer. And yeah, the next word should be the answer. You should try to give the answer. The models are quite good at that when you just train them on predicting the next word. They get better at it when I get to Lecture 9 and tell you about the reinforcement learning from human feedback that's focused on making it better than that. Another thing I want to talk about, because we're talking about scaling, is how much training data is actually needed to achieve these things. And it was interesting when GPT-3 came out and started having these capabilities. They didn't really know how much to train it on. And this table down here shows you what they used. They had 175 billion parameters in GPT-3 before 3.5, and they used 300 billion training tokens. That is, the corporas that they went and hunted up across the internet had 300 billion total tokens. And what was learned subsequently was kind of interesting on this paper here that I'm referring to from Hoffman et al. Was that ratio is wrong. 175 billion parameters to 300 billion tokens. It's not enough tokens. In the chinchilla paper, in the chinchilla model, this came from Google, they showed that a 70 billion parameter model, when trained with 1.4 trillion tokens, they did experiments to see what number here did the best. And this number and this ratio appears to be closer to a better choice. So that's kind of interesting. We haven't really ever talked about how much training data where you learn about law and dental surgery and AP English poorly. That's a key question. And here's some information that comes out of this paper that talks about it. Since that time, Meta has been releasing the Llama series of models. It's now up to Llama 3, 3.2, I think it is at this point. When they talked about the Llama 2 paper is actually it's like the opposite of OpenAI. Meta is very open. This paper is worth looking up, and I'll post it because it gives you all the details of many, many, many things they did to properly train Llama 2. And they talk about the number of tokens there, and they're closer to this ratio. So that's useful to know. Now there's something to understand. This progress has been incredibly rapid to get us from one place to another, from ever better, up to multimodal models. It's just incredible what's happening. And it all comes from this massive pre-training on giant corpora. But there's a bunch of stuff that happened in 2017 and 2018 that is old already in Transformer land. So if you read, and if you haven't been paying attention to my class, you'll hunt around and you'll see, gosh, BERT and Roberta are these transformer-oriented models that are used for classification and even generation. But the problem with them is they're very small. They're only 125 million parameters trained on only 160 billion tokens. And they're trained in a different manner that I have chosen not to cover, but I'm going to say it really quickly. They are not trained to predict the next word in a sequence, given everything that came before. They're trained to predict a missing word or token in the middle of a sentence. So that token is masked out. It's erased and given a special masked token, and the model is asked, and you can do that, to predict the missing thing. What I don't know or understand is whether you need to know more. Do you have to have a better world model to predict a missing word than the next word? I believe, with no evidence to support this, that it's basically the same kind of knowledge you need to predict a missing token. It might be harder to predict the next token. And so I think all of this is a distraction now, because nobody has scaled up these models. They've only scaled up predicting the next token models. And those things just know a lot. They know way more than BERT and Roberta and all its variants are. So if you've touched this field and you've seen BERT, and because BERT was famous in its day, I'm recommending you keep away from it. Just use a pre-trained GPT-2, the biggest one you can get your hands on, or a Llama 2 or 3 if you're up for that, and you can run those systems. And take those models and put a classification head on them or a generation head on them, which I hope you understand now that you're doing assignment 3, and use those to do the thing you want. And the bigger the model you've got, the smarter it is. It'll be better at anything you ask it to do. So that's my recommendation. And I would push against anybody using BERT for these other reasons, frankly, because it doesn't know as much. And I'm going to warn you once again, don't go jumping into the RNNs, recurrent neural networks like LSTMs or GRUs. I've said this before, and train them from scratch. Don't do that without speaking to me or your TA. If you do that, that means you have not been listening in the lectures, because that world has been superseded by this modern world in which world models appear to have been learned, at least according to Ilya Sutskever. I'm going to spend a little bit of time segueing into the project. I've said there's 2 classes of projects. The class 1, which is you train something with data, like in regular machine learning, and the newer way, in which you don't just prompt a large pre-trained model, you actually prompt a bunch of them and you get them to talk to do something really sophisticated. Now, an old school problem that people talk about, and this will show up in assignment 4, is to, given some context and a question, answer the question. So this is a whole thing about, and you can read it, I won't read it, about trees, and then there's a question that relates to this, which is which part of a tree can have vertical or horizontal variation in its specific gravity, if you remember your physics. And the answer, if you read this, is the bole, which is part of the tree. This is a classic NLP problem. It's called question answering. You give context, you give a question, you give an answer. And there's lots of data sets around this, and the goal is to make models that can get these answers. And previously it was common to train BERT and Roberta to do this, and they were reasonably successful. In assignment 4, you're going to see how you can do it with what's called a zero-shot prompt. Zero-shot prompt means you just ask the model to do this, like answer the question, without any hints. You just give it the information. And the reason this will work and is possible because the models do what you ask them to do. It's not clear, I've said this before, but it's not clear what they can't do, actually, and that's pretty interesting. And it has become known that it does matter how you ask it to do what you want, and that is the field of prompt engineering. Prompt engineering is the skill of writing clearly what you want the model to do, but it also comes with some basic insights. You also need some basic insights that I'll now try to convey. And let me do that by hearkening back to assignment 2, where you were asked to build a CNN-based classifier to distinguish between subjective and objective statements. And, I'm here to say you don't really need to do that anymore if you've got a model hanging around. What I'm going to do is, here's how we're going to do it. We're going to write a prompt that says, a prompt to a modern big model that says, determine if the following statement is subjective or objective or subjective. If it is subjective, output sub. If it is objective, output obj. And here's one of the items taken from assignment 2, from the data in assignment 2. The script is a tired one, with few moments of joy rising above the stale material. And as you'll see in a moment, you'll see that GPT-4o is going to output sub, because this is very subjective. The script is tired, that's somebody's opinion, not much joy, stale, all this is clearly subjective. So let's grab ourselves. Let's pull this away and bring this over. Here is, and I'm going to point you at this in assignment 4, here is the OpenAI Playground, which is a different interface that I showed, and I showed some of it in lecture 6, to the OpenAI world that I'm going to point you at. And it gets you access, I showed you something from completions, but now I'm in the chat mode of this thing. And it has something called a system prompt, which is basically you are a helpful assistant. We'll just leave that alone, and you can see right here, let's make this clear so you can see it. You can see this is, I've got exactly what I had on the notes. Determine if the following statement is subjective or objective, etc. And all I need to do is run it and see what happens. And the assistant says sub, exactly correct. Did exactly what I wanted it to do. I told it explicitly what to output, and it just did it. And gosh, it's amazing that you can do that. Now watch what happens, by the way. It's a little bit interesting. This model is GPT-4o over here. There's a lot of choices you can pull down here, but GPT-4o is kind of the main one these days. So if I were to get rid of this, you'll see something that is... so I'm not telling it how to output. Just say determine if the following statement is objective or subjective, and I'm not saying give me this one answer. Watch what happens. It gives me an English statement, says the statement is subjective. That's the same answer. But it actually gives an explanation. It automatically gives an explanation. This is a relatively new thing that it says. It expresses an opinion about the quality of the script using words like tired, few moments of joy, and stale material. Exactly how I would have analyzed this, actually, which are open to personal interpretation and preference. So it is explaining its answer to you. And this is a new property of GPT-4o, that it definitely goes there and explains things. And I'm going to kind of talk about how that came about. We could also, I'm going to show you, maybe I'll kill this. And let's see what happens if we use O1 preview, which is a super sophisticated model. Let me run it and see what happens. See, it says thinking. And this model is actually leaping ahead and gives a very detailed explanation of what's going on. And then ultimately lands on the answer. And it's using something called chain of thought. And it's actually doing something more than that. The previous one was using chain of thought, probably. This one is not only producing the answer, it is reconsidering the answer, and it's got some prompts that we can't see, but we know, or we intuit, that OpenAI is telling the model in an agentic fashion, look at what you produced and think about it and begin to explain it. And it iterates on that, and it's more expensive, by the way. It blasted through 526 tokens here. in doing that. And so this O1 creature is a whole new kettle of fish, costs more, and everyone I think is still getting used to it. I could show you more examples, but you get the idea that sort of the core thing I was trying to show is, and let's go back to this, is you don't have to train a strange looking classifier. It's like with a whole pile of data. You just ask for it. And these models are so smart, they will do what you ask them to do. And if you haven't picked that up, I mean, you sort of picked it up because you use the model, use ChatGPT to solve problems, but you can retrofit every old problem into a prompt, and it's probably going to work. Now, in your project, you're going to have to show that it does work. And so, yeah, that's something you'll have to learn. There's another example here. I'm not sure I'm going to spend too much time on this one, because this is about my research. Yeah, I'll just leave this here for you to read in the notes. This is something directly from our research, with a longer prompt that says, I want you to act as a therapist and listen to what somebody says and reflect it back in a certain way. And that's what this example is talking about. And so I'll leave that for you to read in the notes. Here I want to give to you a methodology for creating the prompts that you may use A in your project and B in assignment 4. This is taken from assignment 4, which is not out yet. Yeah, let me walk you through it. So now there is no more training data. There is only test data. Test data tests to see if your prompts work. So, and here's how we have thought about it. In test data, you also think about having hundreds or thousands of things to test. You don't really need that anymore in the prompt engineering world. So let's begin. You've got this thing you want to do. You want the model to do. Let's say classify subjective or objective. The first thing you should do is write down what your criterion is that makes the output correct or acceptable. Here I'm not just talking about classifiers. I'm talking about generate sentences that make me happy. Generate jokes, or any of the million things you want. But you need to know in your mind what it is that makes the output acceptable or not. So you should just write that down as if you were talking to a friend. You might need to look up the definition of one or more words if you think that the model doesn't know the definition of those words, or exploring online resources. If you're doing a project, say, around evaluation of speech by someone who's got speech impairment, then you need to look up the criterion by which quality speech is judged. So you have to walk into the world that you're working in and understand it. Actually, you can't just be an engineer. You got to walk into that other world if it's speech deficits, for example. So regardless of whether you're doing classification or generation, you need to know what makes your answer good. And then, based on that, write a prompt that says, do the following thing. If it's processing data, you say, do the following thing on this data, like the classifier, and try it. And then that's what step 3 is. Just using just one input example. Take that prompt and run it on that one input example. Now, once you've got it working, or you run it on that example, and then you try to make it work on that example. So step 4 is keep evolving the prompt by changing the English. If you see something wrong, you can say, oh, it's doing that, so you're saying, don't do that. You can say, don't do that, or you can try to say, no, try to do this in the prompt, and be more precise about it. One golden rule here is that you must not use language that is specific to the input data. That is, if you see the coming out, turn it into an and. Like, you can't, or if you see something specific in the input, if this is in the input, do that. The reason you don't want to do that is because that's specific to the input. It's like overfitting again. But if you don't use language that is specific to the input, then you have this beautiful thing that's possible. That it allows the prompted model to generalize to other other examples. Yeah, that's kind of a neat piece of all this. So you make it work for one example with general words, and once you've made it work for one example, then make it work for two using the same basic method. You may have to keep adjusting because there's something different about the second example. Make sure the second example is quite different, and then just make it work for the second example. And then after that, take 5 different training input examples all at once and see if it works on those 5. And count them. And so at that point you've got 7 examples, and you can calculate the success rate, which you'd like to be 100%. And then after that, if it didn't work, then you evolve again some, and then you run on a larger set, like 20 holdouts test examples. 20, which is a small number. So measure the success rate of that yourself with human labeling. You say yes, good, or no, not good. And calculate that success rate on, that would be 27 examples that you could measure it on. You could say whether they work. So the thing to notice about that is a test set, when you are training a model with thousands or millions of parameters, it has to have thousands or tens of thousands of examples. In this case, when no parameter is being trained and you're simply writing a prompt that gets you where you need to go, you don't need lots and lots of examples. If it works on 20, it's probably going to work on the next 25 too. So it's really a different world with some of the same concepts, like the concept of generalization, which turns into don't write anything in the prompt that's specific to the input. And step 8 is, if you don't get 100% success, then keep iterating and see what, look at exactly what went wrong with the answer and try to change the prompt so that they all work. So that's my method that makes a ton of sense to me about how you do prompt engineering. In my own research work, this was from a year ago, we were 98% successful in generating the kind of language we wanted to generate with GPT-4. There's some posts that I'm linking to here that give you some advice on prompt engineering. And what I've just described to you is what is called zero-shot prompting, where you just tell the model what you want to do, exactly what I just described. And over here, here's an example of what's standard prompting. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. He has 3. Each can has 3 tennis balls in it. How many tennis balls does he have? And it says the answer is 11. And so this is few shot prompting, because this is an example. This here, let's circle it. This here is an example of what you want the output to do, and then here's the actual question you're asking it. The cafeteria has 23 apples. If they use 20 to make lunch and bought 6 more, how many apples do they have? So the answer should be 23 minus 20 plus 6. That should be 9, right? And so this is wrong. That's called one shot, because there's one example. This is the new method that I want to describe, which is chain of thought, where in this example they show the model how to work out why the answer is 11 here. And it says Roger started with 5 balls, 2 cans of 3 tennis balls. Each is 6 tennis balls, so 5 plus 6 equals 11. The answer is 11. And so here's the same question here, coming over here, but now it's been taught to do, or shown how to do to think it through. And so here the answer is worked out. The cafeteria had 23 apples originally. They used 20 to make lunch. So that leaves them with 3, and then they bought 6 more. That gets them to 9. So it got the right answer. So this was one-shot chain of thought, because it's showing the chain of computation. And so this paper that I'm linking to describes all of that. That's one of the original papers on what's called chain of thought. And one way to evoke the chain of thought is to show it examples of it with the few shot. There's another way, which I actually think is better, and that is back to zero shot, where the instruction says show, in addition to whatever you're asking it to do, you say show your steps towards an answer, or think step by step. And if you do that, it's been shown that you get a better answer. When you make a model think something through, and remember what's happening, it's thinking through things, and that thinking through gets put back in the auto-regressive loop, back into the input. And so that information is being used to generate the next thing, ultimately to the answer, and that information is guiding the model to head towards the right answer. At least that's the thinking behind this. So this is such an important concept that it's now considered to be the thing you will always want to do. You always want to ask for the explanation for something before you get the answer, or the step-by-step before you do the answer. And this is so important that I think what's happened in the last year is that it may be that you don't need to do this anymore for GPT-4 or 4.0, that it automatically has been kind of trained to do this first. And I think we saw that a moment ago in the example I showed you, where I when I kind of unleashed it and didn't say just produce subjective or objective, it actually went through an explanation. And so that's kind of interesting, GPT-4.0. GPT-4.01 is a whole new creature. It's just got a little one on it, but it goes even farther in that I think it's clear that there's multiple LLMs in play, or at least the LLM is being asked to reconsider its output and think through it in a more deeply critical way. So the answer comes out, and then the model goes, I'm going to think about this. Are you sure you got this right? Are you sure you got that right? I mean, I don't know what it's doing, but it's gone into some other loop. If you read about 01, you'll see that I'm talking. There's some version of that going on. Again, OpenAI is not open. They don't tell you. But that's what's happening with 4.0. And if you go back and look at the example I showed you a moment ago, then you'll see that as well. And this was something that was all the rage last year around this time. Apparently, if you told the model to take a deep breath, it would be better. Its answers would be better. And you have to come up with a reason why that might actually work. Now, another thing I just want to comment on briefly is what's called the system message that you'll see on the GPT Playground. And it is the overriding command that the model is supposed to be paying attention to while it's doing everything. And the generic system message, as you saw when I was showing you the Playground, it was, you are a helpful assistant, which is pretty generic. But you could say, you are a chatbot that is trying to help people get over their anxiety. So that would be the kind of present command that's always being presented to the model. They never actually tell you what is being done with this separated system command. Some schools of thought think it's something that gets repeated into the input context. Remember, everything that we're talking about just has to go into the input embedding context that I've been talking about in the other lectures. So this gets, the system message gets put there at the top, and then maybe the user message comes in, and then the system message gets repeated. You don't see it, but it's put into the context over and over again, so it's ever present. That's some of the thinking. It's not really explained very well. In our own research, we have noticed that this is a good place to put the overall command. There's something that is done that does make it more authoritative. Okay, another thing I want to talk about is the fact that in assignment 4, when I get it out there, you'll be using the API access, the programmatic access to GPT-4, and probably GPT-4.0 is the main one we'll be working with. And you'll be using it to learn how to become a good prompt engineer for that assignment and for perhaps your project. And the key message here is, and one of the reasons to push you towards the Class 2 project is simply this, that you want to be using this most powerful thing because it'll do what you ask it to, and you don't have to train it with lots and lots of data. It's kind of why I find it compelling. Okay, Two last things I want to talk about. I think it's two. Here's a very important term. That is how many things get done nowadays using large language models. And it's got a name, and it's called retrieval augmented generation. And the idea is that you wish to get answers to questions about some specific information, specific text. But it might be in your application, you don't know where that, you don't know which piece of specific text the answer should be drawn from. And rather than putting a giant document into the context, because that costs money, every token costs money, if not real money to OpenAI, then computation time, then wouldn't it be better if we could accurately pick the right chunk of text that we knew had the answers in it? And we can, actually. Other parts of this course have taught you how you can create embeddings that characterize chunks of text. And a really common thing that's done in retrieval augmented generation is you have this massive set of text, say it's some encyclopedia, and you have a query that says, I want to know about bicycles. Prior to all of this, you would have taken the section on bicycles and created an embedding around it, and you would create an embedding around the query, I want to know about bicycles, and one would match to the other. You'd see how close the embeddings were using cosine similarity, say, and you'd pick the closest to one or several, and take that text, throw it into the context as input, and then ask your question. Tell me about how bicycles, why they don't fall down, would be the question. And so you retrieve the information from some data set that you know about and plop it into the context, and therefore augment the ability of the model to answer the question, because you just told it a lot of things where it can find the answer. This is actually a very deep and interesting thing, because if you think about it, there's two forms of knowledge going into the large language model. There's what got trained into the parameters, and then there's what you put into the context. And and those things might contradict, and so, or they might not, but you can use the ability of one, which might know how to look for things, to extract information from the other. RAG, or retrieval augmented generation. The second thing I wanted to talk about super briefly was tokenization. I've avoided talking about it. You've dealt with it a little bit in assignments 1 and 2, where we've pre-processed the inputs, but we haven't really chopped it up into tokens. In assignment 3, there was a tokenizer. You can see it, the GPT-2 tokenizer, or the MinGPT tokenizer. And it is an algorithm that figures out, given a corpora, the best pieces to break the input into tokens, which are less than whole words often, although they may be whole words. So a tokenizing algorithm analyzes a corpora and then chooses the set of tokens that are then usable. It turns out that often, at least some of the tokens are all symbols and all letters. And what's good about that is it means you can take any word you haven't seen before and build it up by creating tokens that are just the letters. So you're never going to be stuck in tokenizing your corpora, because you've got the symbols and the letters. The algorithm that determines what is the set of tokens you should use, that was often used up until very recently, is called the byte pair encoding algorithm. And I'd like to send you to the Jurafsky textbook, section 2.5, and ask you to go learn that algorithm so that you know what's going on. And understand that tokens are sometimes full words, sometimes part of words, and some tokens are meant to be attached to other tokens to form full words, and some are not. And all of this allows things like this to maybe not be a token, but to be interpreted. LOL. If you talk to ChatGPT, you'll see it understands lots of acronyms that are in the common usage. Okay, I'm going to end lecture 7 there. The last thing that's here is an example of a very lengthy prompt that we used in our research, so I just wanted you to get some sense of how complex prompts are. But hopefully you will find this lecture useful. It's a lead-in to assignment 4, which will be out in a week or so, and it's helpful for your project thinking. Thank you.